Okay, so let's actually go ahead and work out the derivative function for f of x equals x squared, and we're going to differentiate it by first principles. Now, we're going to keep it abstract, so we're not going to use any numbers anymore. We're just going to use x's and h's and so on. Okay, so let's start off with the following. Okay, so there's your x, then you fix a distance h across, and that's your x plus h. Okay, and let me write that again, let x plus h, right, and this would be your f of x, okay, and then this would be your f of x plus h, and then the idea was to take the limit of h getting really small of f of x plus h, take away f of x and divide it by h. Okay, so here's your right angled triangle, if you recall. Okay, you join this up, make a right angled triangle like this. Okay, that's your f of x. Subtract f of x is your vertical step, and then your horizontal distance is whatever h is at the time. But we're going to do it algebraically now. What we need to do is, because we know what our function is f of x equals x squared. So what we need to do is actually work out what this numerator on this fraction is going to be. Right, now, first of all, f of x just equals x squared. So what would be f of x plus h? Well, I would take this, I would take this and I'd put it into my function, so it would be x plus h squared. So what I'm actually doing is this. To work out the derivative function, the f dash of x, okay, remember I'm taking the limit of h getting really small of f of x plus h. Let me write again, f of x plus h, subtract f of x divided by h. Well, that is the limit of h getting really small, close to 0 as possible, x plus h squared, subtract, well, what's this? Well, okay, sorry, that there is just x plus h squared, and this is just x squared, and I'll have to divide it by h. Now, well, let's actually work out what this is, because we can work out all of this. Well, what is x plus h? Well, my handwriting's terrible at the moment. What is x plus h squared? Well, okay, that's double brackets. Remember, x plus h, that's x squared. And if you do this bit yourself, you should get 2x h plus h squared. So I'm just going to replace this bracket here with the expanded version. Okay, so let me write it over here. So limit of h approaching 0 of, okay, big fraction line, and it's x squared plus 2x h plus h squared, subtract x squared, okay, that's that x squared there, okay, divided by h. Now what happens here? Well, let's see, some things get removed because the x squared is being taken off, right? So that x squared and that x squared cancel each other out, and what you're left with is the limit of h approaching 0 of 2xh plus h squared over h. Now what happens here? Well, if you think about it, from this numerator I can factor out a h, can't I? So if I do it again, if I just write limit and then you can fill in the bottom bit, you should always write h approaching 0. Okay, I can factor out from here, there's a h there and a h here, I can factor that out. So the h squared there, h there, so h can come out. I have a 2x plus h over h, right? Now, these two cancel each other out. Okay, so I'm no longer dividing by 0, right? I'm no longer dividing by 0 because I've got no h's on the bottom. But what am I left with? I'm left with a limit of h approaching 0, and all I'm left with, no more fractions anymore, I'm left with 2x plus h. Well, what happens now if I make x 0? Well, actually I can make x 0 because I'm not dividing. I'm sorry, if I make, not x 0, if I make h 0, what happens now? Well, if h becomes 0, all I'm left with is just 2x. So what I've actually found is my derivative function. My derivative function is f dash of x equals 2x. This is the derivative function for x squared. Okay, that's because I'm no longer dividing by 0 here when h gets really small, because the h's all cancel themselves out and there's no h's left on the bottom, and all I'm left with is 2x plus h. Now if we go back, that's going to help us work out the gradient anywhere on my graph. So here's my function. So this is f of x equals x squared. Now I want to find the gradient at, so I know my derivative function, I know my derivative function is f dash of x equals 2x, okay? I know my derivative function, so let's say I want to find the gradient at x equals 1. So what's the gradient of this pink line here? Well, all I need to do is put 1 into my derivative function, so I need to work out f dash of 1. So I do 2 times 1, and that's 2. That's exactly how steep that line should be. At 1 on this graph, it should be 2 units. It's too steep. Okay, it's too steep. Well, it's steep. It's 2. Okay, or if I want to work out the gradient at, let's say, minus 2. So what's the gradient of this tangent line at minus 2? The derivative function does it for me, so I don't need to do it by I anymore. I just need to do f dash of minus 2. So bung minus 2 into the your function. So 2 times minus 2, that's minus 4. So this, and it even tells you it's a negative tangent. Look, it's going downhill, so it's negative, but it's negative 4 steep. So you've just worked out the derivative function for this. Okay, so, and what we've done is we've done it by first principles. Okay, so we've basically done this to it, okay, and we've just cancelled all the h's out, so we're not dividing by 0 anymore, and we're left with something that's nice and neat. We're just left with 2x. So the gradient function for this one, for f of x equals x squared, is 2x. Okay, there's a connection between the two. You can go from one to the other. Maybe you can spot that connection, but that's the derivative function there in a nutshell. Okay, now I'm going to do some more examples in the next clip, so stay tuned.